All right, so today, Tuesday, April 7, 2020, we will be able to identify and explain effects and uses of aspirin and penicillin. So last class we had an introduction to drugs and medicine, and throughout this unit we're going to learn about kind of the famous drugs and medicine and learn about its history and typically how they were discovered and their uses. So that format will continue as we go through all of the new sections. So as you see here, we're going to look at aspirin and penicillin first. Okay, I want to do some quick announcements and then we'll move on. As for the assignments, after this section, read and do the exercises of this section, which is numbers 6 through 9, and then read the next section on opiates, which is 879 to 884. Okay. In terms of announcements, I mentioned this last class, but please try to be involved as much as possible. I know it's really difficult to kind of keep your head straight, especially when it's kind of unfair for you as the senior class, and as your advisors, myself and Ms. Nguyen, we really feel for you. We know that it's mainly unfair, but the way I look at it is you have to make the best out of your situation, and try to keep involved as much as possible. So ASB and Ms. Yohara and the leadership are really trying their best to keep you involved, both as a school, but also as your senior class. So please keep up to date, because you need to be involved. Try to stay involved, all right? So April aftermath, this is kind of summarizing and kind of wrapping up March Madness Spear Week. So this week is Spear Week. So yesterday was Make a Fort Monday. I actually made an Instagram for the sole purpose of trying to reach out to all of you and keep spirited and keep you all involved for the rest of the year. If you look at your Instagram at the 2021, I think you'll see my fort that I made there. Today, TikTok Tuesday, record a TikTok dance challenge. Tomorrow, Wicked Wednesday, record video or take a picture of your most wicked trick. Maybe that just shows you doing something interesting or a skill that you did. Thursday is Theater Thursday. Watch your class movie. So that for us, that's Suicide Squad. Maybe you can try one of those Google Hangouts or alternatives and you can watch the movie together with your friends. That would be pretty cool. And then Friday's class color. So wear crimson. Take a picture of it and then again send it to our class's Instagram. All right, so moving forward, aspirin, quick introduction. Again, this is kind of how our body works. Our body's ability to perceive or feel pain is one of our best defense mechanisms. Right? If you think about all of your experiences, if something typically causes you discomfort or pain, you most likely stop, right? And it's actually a problem, and there are people who, like let's say they put a hand in a fire flame, they won't feel that pain, but the physical aspect is still going to happen, but because their brain doesn't tell them to stop, it's actually a big problem. So the side effect, of course, of feeling pain is that it's unpleasant, the fact that you do feel the pain. But that's okay. We have developed medicines to help stop that pain. But first, let's look at the process. So there's a site of pain. Let's say you sprain your ankle. So that's the site. Your ankle gets hurt. Maybe you're jogging and you roll your ankle. Once that happens, I know this sounds almost instantaneously, because once you roll your ankle, you instantly feel that pain. But if we try to slow down time, this is all happening, and maybe you start to appreciate how complicated and how kind of wonderful our body is. So once let's say we roll our ankle, our body releases chemicals, and these chemicals have a specific name. We call them prostaglandins, but let's just focus on the big picture. Once it releases those chemicals are in our body, and they're able to attach to our pain receptors. So they activate our pain receptors. And remember, these receptors are there to send a signal to the brain. And as you can imagine, once it goes to the brain, it tells us to say, ow, and we feel that pain. So if you think about how aspirin works as a pain reliever, we need to figure out how to stop one of these processes so that we don't feel the pain. So how aspirin works is it's an analgesic, our fancy chemistry term for a painkiller, and it prevents the stimulation of nerve endings and release of prostaglandins. So if we can stop the signal to the brain, we won't feel that pain. Or if we stop the release of the chemicals, we also won't feel that pain. It doesn't mean that our ankle won't still be swollen. It's just we won't feel the unpleasant feeling of the pain. What's also cool about aspirin, it's an anticoagulant. Coagulant means to clot up, so it reduces blood clotting. So an anti means that it reduces the clotting, but the side effect is if it doesn't want to clot, it will do the opposite, and sometimes it increases bleeding, especially if you don't want to bleed. There's also some synergistic effects with alcohol. So definitely people say don't drink alcohol while under medicine because it increases its effects. Maybe it's better at removing the pain, but then now you start seeing side effects. Maybe you start bleeding somewhere else. Maybe you start having ulcers, where your stomach has openings in the skin. Let's look at the history of aspirin. So Bayer, I'm sure you know different brands of painkillers, maybe Tylenol, but Bayer is the originator. It was the one who kind of invented it or made it for the first time. So they synthesized aspirin from the esterification of salicylic acid. So that esterification of salicylic acid should sound very familiar, and it's because some of you made this in our ester lab, depending on which alcohols and carboxylic acid you chose. So on the left is salicylic acid. Notice how it has the OH on the bottom right, that's our alcohol, and then you added it to acetic acid, and those two combine create an ester, which you see on the right. The right side is aspirin. On the left, salicylic acid was actually found to be a good pain reliever, but it had a lot of downsides, and the downsides is that it causes you to vomit or throw up, and it tastes bad, and maybe because it tastes bad, it made you throw up. So on the left, while it was effective in reducing pain, a lot of people didn't like the downsides, and it actually made the downsides much more intolerable than its benefits. So what Bayer did, and it's kind of interesting because you did this in a lab, actually did it very easily, was able to create aspirin. And aspirin is the drug we know today. It's still a pain reliever. I don't think most drugs in medicine really have a good or bad taste, but we know that it's okay and that it's tolerable now. And this is one of the most widely used drugs. It's one of the top 3 drugs, if I'm not mistaken, that are sold worldwide. In terms of looking at these two, how can we tell the difference? Well, it should make sense. Different chemicals means that they have different properties. So again, here are the two chemicals. On the left we have salicylic acid, and on the right we have aspirin. We can use something called a melting point. Remember when solids turn into a liquid? So on the left here, salicylic acid has a melting point of 159 degrees. And on the right, we have aspirin, which melts fairly lower, maybe about 20 degrees lower, 138 to 140. I want to show you a little bit of what this looks like. So I use this a lot actually in my research. We take this really, really thin test tube and we put some of the chemicals in here. I'll put these as dots. So let's say this is salicylic acid. I'm going to put this into an instrument that heats this up. And because we have a thermometer, we can tell the exact moment that this solid is going to melt, because we know that the solid I don't know how to draw, is going to turn into a liquid. So the moment we see that turns into a liquid, we know that our thermometer says if this is aspirin, or sorry, we said salicylic acid, we know that this thermometer might say 159 degrees Celsius. So this is now a liquid. So hopefully that drawing kind of helps you there. We also learned that because these are different chemicals, they actually have different functional groups, and organic chemists have a way to distinguish these functional groups through another thing called an infrared graph. It's able to use the bumps and peaks as a way to detect functional groups. So again, this is just more of a a holistic big picture idea. So on the left, this is salicylic acid. Notice how there's different peaks here. On the right side, we also have aspirin, also different peaks. If you look at the region on the left side, there's a lot more peaks, and those two peaks, it's kind of colored. On the left, I think this is gray, and then there's red. These represent the two OH groups in salicylic acid. Notice how salicylic acid has two OHs. And this is different from aspirin, because aspirin only has one OH, but you'll notice it has two of these C double bond O groups. So if you look in this region over here, I think this number is about 1700. You'll see that, again, if you look at the gray and red peaks, there's two peaks that represents the two C double bond O's. Cool, so now let's look at modifications. We talked about last class that drug design is important in making medicine. On the left again is aspirin. Aspirin, because it has that OH thing up there, is actually an acid. And this is an acid-base reaction, right? NaOH is a base. In it, we learned that acids and bases create water and also a salt. So on the left, aspirin is actually not sold this way throughout the world because it's not soluble, which means our body can't digest it. But when we modify it to have the sodium, we now create an analog that is a sodium salt. Because the salt is more ionic, right? The O is negative, the Na is plus. That means that it's more soluble, and that means we can digest it. So a very simple reaction from taking something not soluble to something that is very soluble. And what you see on the right is how aspirin is sold almost the same way throughout the whole world. now that we've done aspirin, let's do our second part of the lesson, penicillin. So to introduce penicillin, maybe some of you have taken penicillin before. It's an antibiotic. Antibiotic means it's a medicine that destroys bacteria. So in light of what's going on right now with the coronavirus is a virus. So that means antibiotics are not good against viruses. And it's only against bacteria that it's good against. In terms of where penicillin comes from, it's actually produced by microorganisms, so different species in the world we found create penicillin. And then just a really simple picture of what penicillin looks like in pill form. History and discovery. So in 1928, microbiologist Alexander Fleming noticed that a fungus, it's mold, known as Penicillium notatum. Notice how the Penicillium notatum is the species that creates penicillin. So everything sounds similar, but we kind of do it to try to make things, relating, so that we don't have to make, obscure names. Anyways, he contaminated some of his own research, and he was researching bacterial colonies. And he noticed that it inhibited and stopped growth, and he published its findings. So if you reread what we just mentioned, he had a mistake. He accidentally dropped some of his penicillium species with some of his other colonies, and by accident, or from his mistake, he actually discovered one of the most widely popular and effective antibacterial agents. So here's I look back at his original notebook, and here's a petri dish. So for those of you who remember doing this your freshman year, at the top is the Penicillium species, and then on the bottom was his research, his other bacteria species. And what's really interesting in the center, in between, you'll notice that the specks in the middle are really, really small. So he kind of realized that it's stopping the growth of the bacteria. 13 years later, two different scientists, Florey and Chain, isolated penicillin as the antibacterial agent. So penicillin is the compound that they found from the Penicillium notatum species. And this was revolutionary because during the time it was heavily used to treat bacterial infections in World War II, saving thousands and thousands of lives. And in 1945, Fleming, Florey, and Chain, because they all did research on this, shared the Nobel Prize in medicine. So you see Fleming on the left, Florey in the middle, and Chain on the right. Let's now see how it works, the mechanism. How does it work? So 1945, Dorothy Hodgkin. I always think this is really interesting because we don't get to hear many female scientists that often. And she was one of the main contributors for why it's so useful for us today. She was able to figure out the structure of the main chemical in this mold. Again, we call it penicillin. There's many different penicillins. We just happen to call this penicillin G. You can imagine there's penicillin A, B, C, D, E, F, and G. But this one happened to be the one that was the one that stops bacteria. Kind of interesting, but if you look at the shapes, there's in the center, and this is the big thing for penicillin, is the square-like structure. So penicillin contains this four-membered ring structure, the square, and it contains an amide group. So if you remember the amide, it's a C double bond O attached to an N, which is known as a beta-lactam. This ring, like a square, has 90-degree bond angles, making it have a lot of strain. In normal conditions, we would have taken out the chemical structures, and I would have had you try to create this four-membered ring, and you would have realized that it's very difficult to push those bonds together, making it have a lot of strain, and that you will realize that it really wants to break open. So that's kind of the main job of penicillin, is focus on this. This square-like structure wants to open. So I want you to keep that in mind as we talk about the next section. So if you can read it at the top, penicillin bacteria. I made this dramatic, so hopefully I'm trying to show you the history of what's going on between this war between humans and bacteria. Because we are humans, we're gonna write history on our side of the humans. We are the good guys, and the bacteria are the bad guys. So, bacteria has an enzyme called transpeptidase. Again, don't be wrapped up on the chemical. Think about the big picture. But transpeptidase is responsible for the formation of cell walls for bacteria. So bacteria has an enzyme that helps them live because it helps them form their cell walls. So think about whose side is which. Bacteria, transpeptidase are allies. The beta-lactam antibiotics, such as penicillin, stops this enzyme. So this is our side. This is the humans, and we are allies with the antibiotics. We've created that medicine to fight against bacteria. So I will try to do this and draw it out again. But on the left side is penicillin. And we learned that its square, that beta-lactam, wants to open up. So you can see on the right side, it starts to open up. I will try to shorten what the enzyme looks like for the bacteria, and I will label it R2. So if you notice on the left side, there's a bunch of R2s lying around. Let's say in your body you have a lot of bacteria. The bacteria has a lot of R2s, and because we're sick, we take penicillin. So now penicillin is in our body. Notice now on the right side, the ring has opened, and if you look very specifically to the ring, it has grabbed one of the R2s. Penicillin open its ring and grab or bind one of the enzymes, R2. Remember, the enzyme is on the side of the bacteria. The penicillin is on our side. So, when you take penicillin, it opens up and grabs the enzyme, and it prevents that enzyme from building the cell wall for the bacteria, and therefore the bacteria dies. Okay. So now, the resistance. You learn a lot in biology, survival of the fittest, and this is exactly what happens. Bacteria die over time, and then the ones that live are the ones who have evolved to fight back against our weapon of penicillin. So the antibiotic resistance, bacteria fight back. So kind of recapping, the beta-lactam, that square, is very important for us because it has antibacterial effects. And you can imagine it will lose its effectiveness if that ring is broken and no longer able to grab that bacteria enzyme. So bacteria have evolved to show resistance, and they produce an enzyme. I'm going to call this a dummy enzyme. It's kind of like a diversion. It's like a trick for the bacteria. They call it penicillinase, which opens the ring and makes it inactive. So I want to try to draw this again. I need a lot of space. So let's draw the first scenario. To make things simple, I'm just going to focus on the square. This is the beta lactam. This is the N, and then here's the C double bond O. So this is in our body. This is our penicillin. Let's say the bacteria creates an enzyme called transpeptidase, which we will abbreviate as R2. Remember, let's kind of whoa, I should have done this at the beginning. But let's summarize our sides of the war as my analogy. So the good guys is us, humans. I'll keep this in black. And we have penicillin. And the bad guys we have bacteria, and we have the transpeptidase. Or we've labeled this as R2. So good guys, bad guys. So what happens is the beta lactam opens up because it wants to open up. The square is very strained, and it will grab onto one of these R2s. If it's grabbing R2, maybe I'll draw the other 3 because I drew 4 total. R2 is no longer able to help bacteria create its wall. That means it dies. Bacteria dies. So we win. Here's the next scenario. Now our bad guys, they evolve. So here's another scenario. Beta lactam. The bacteria are smart. They evolve. They still have their R2. Remember, this is what they're helping to help them build their cell wall. But they realize they evolve that penicillin grabs onto them. So what bacteria ends up doing is they start making these dummy enzymes. So now we have the dummy enzymes are also on the side of the bad guys. So what happens, and you can imagine, same thing, our beta lactam, our square structure opens up. And now instead of grabbing one of the R2s, the bacteria have effectively tricked us and the penicillin, and now have taken the dummy enzymes. So there's still dummy enzymes around. So you'll notice it didn't take any of the R2s. Remember, the R2 is the one helping the bacteria. So R2 is left to help bacteria. Bacteria lives. So we can say bacteria win this round. Okay. We'll go back to this because we're not done yet. Because again, we're the humans. We want to make sure that we are safe. So this is kind of my dramatic finish. The antibiotic resistance. Humans fight back once again. We can make penicillin analogs. Remember, these are changes that still have that beta-lactam, but we've modified that confuse the binding of that dummy enzyme. So on the left here is methicillin. Notice here's the square thing, but then on the left we added some stuff to it. And then on the right side, a little bit different, but it still has the square, and then we added again more stuff on the left side. And this is a way to confuse the dummy enzyme. So let's go back to our last picture here. So here's us again. Here's our beta-lactam. And then over here, I'm just going to say we added this huge structure over here. So what is the good guys? We have analogs also. And let's draw the bacteria. Remember, they still have the R2s. They've still evolved to have the dummy enzymes, but we've created this analog, and you can imagine it does exactly what it did in the first place, which is to grab the R2s. For whatever reason, this little chain over here allows us to detect the R2 versus the dummy enzyme. So then we're back to the beginning. Bacteria dies. And then we win again. And who knows, maybe in the next 10 years, bacteria is going to evolve again. That makes these drugs no longer active. And then it'll just keep going back and forth. We'll make something better. They'll evolve, and so on and so forth. So I think it's pretty interesting how this works, but that's pretty much it for this. And then again, here's the summary slides. I'll record this and upload it to YouTube. And then again, the assignment for next time, read and do the questions of this section, 6 through 9, and then page 879 to 884 is the next section on opiates. So opiates is like heroin, codeine, morphine, so interesting stuff. Yeah, other than that, hope that you're all safe. Please contact me if you need trouble or still need help on your IA. Yeah, I'm here for you. Please utilize those resources. I'm available. Okay.